First of all, I'd also like to thank the organizers for inviting me to this wonderful workshop on integrability in condensed matter physics and quantum field theory. So far, I haven't heard anything about condensed matter physics in this conference, actually, and I will probably be, or almost nothing, I'll probably be the first to say something more about it, although this will also be connected with quantum field theory, hopefully. I'm talking about something which we call thermal form factor expansions of thermal form factor series, and this refers to using a different basis than which is often used, not the basis of eigenstates of the Hamiltonian, but the basis of eigenstates of what we call the quantum transfer matrix. I'll explain that in detail, hopefully. And I think this is a subject that I did almost exclusively with my courses. Nobody else was doing such things. So I'll probably have to explain many things, but the main purpose of this talk is to connect it with some things which were done by my friends for a long time, namely with the fermionic basis, right? This is one thing, and then I want to show you some of the older work I did, say, 2 years ago with my collaborators on applications for the XXE spin check. So I'll give you a short introduction. I have developed a habit to give long introductions, but for this expert audience, the general introduction will be short. I'm glad about that. I will explain you what the thermal form factor series is for dynamical two-point functions, and then I'll explain you something of what I call another factorization. So we have heard about factorization in Hermann's talk, in Fjoler's talk, and in Holger's talk. So this was factorization of density matrix elements or correlation functions. And here, inside this form factor expansion, I'll show you that naturally another factor splits off, which is independent of the operator. And this is an object we were able to calculate in a special situation. We were able to calculate it very explicitly. This is the what I call the universal amplitude, of course it does not depend on the form factor, and this is opposed to the part not depend on the operator, as opposed to the part which depends on the operator, which is a properly normalized form factor. This will be connected with the fermionic basis. This gives you beta ansatz results in this part. And so this allows us to look at the XXE chain and the massive antiferromagnetic regime, so delta larger than 1 in my normalization. So this is where you have the two Ising-like degenerate ground states. And then I'll summarize. So of course I didn't do this alone. So this application part and the part on the universal amplitude, as I said, is already almost 2 years old, and this was done in collaboration with Konstantin Babenko, Karol Kozlowski, Jesko Zirka, and Joji Suzuki. And the new things I'll be reporting is work in progress with Karol Kozlowski. So here is our general introduction. I was several times asked actually to give talks to mathematicians, and then I thought it's good to give the definitions of the objects. So it's about statistical mechanics of quantum chains. These are objects which are discrete in space and one-dimensional, first of all. So I have a Hilbert space, which is a tensor product of local spaces, C to the D, and any endomorphism on this space I may call Hamiltonian if I like, and there are local operators which are get by taking an operator in one of these spaces and tensor it with the identity. So then, what is quantum statistical mechanics? Once you are given Hamiltonian and the space of local operators, so they multiply and add them, so they give you a space. Then you want to know how the local operators evolve in time. They do that by Heisenberg time evolution, by a joint action of this time evolution operator e to the IHLT. And then you want to do experiments. You evaluate operators, and you do that using a density matrix. And the canonical density matrix of statistical mechanics means to take an expectation value, which is the trace with the statistical operator divided by the partition function. And once you know that, you can describe all reality for condensed matter systems. So almost all experiments which are done are in the linear response regime, and there you do, say, time-dependent perturbation theory of first order. What concerns the interaction of your system with your apparatus. This is assumed to be small, and that's why almost in all experiments, first order perturbation theory is justified. Then you get something which is called Kubus theory in condensed matter physics. So that means you connect all experiments, all kinds of experiments, with dynamical correlation functions at finite temperature T. So what you have to calculate, you have to combine those two things. You have to look at, for instance, 2-point functions. So one at time 0, and then the other point, the other operator, you time evolve, and then take the average with your density measure. That's the whole game. And if you do certain scaling limits, you can transform this into quantum field theory. And this is very simple. Everything is well defined for mathematicians. So the only thing everything is finite here. So the only thing you have to justify is that you can do this limit. And this is for a very general class has been justified in the 60s, right? Okay. So I will be talking about integrable spin chains, and first I'll give you some general results, but when it comes to concrete calculation, I will refer to the XXZ Hamiltonian, which I don't have to introduce here. It's just for the notation. I'm using the parameterization that delta is cosh of gamma, and Q, which also often appears as e to the minus gamma. And the main goal of all of my research over the last years, and probably I won't be able to do much more before retirement, is to calculate such correlation functions which depend on temperature and time and space, explicitly for all values of space, of time and temperature, and all parameters, right? For instance, for this model. And unfortunately, this is not done. And also for almost none of the integrable models. Actually, the only model that I could be happy with is the X model when delta is 0. This is sometimes called free fermion point. And at that point, there is, for instance, a beautiful result of the sigma z correlation functions at different space-time points and at finite temperature. You see, this answer is kind of optimal case. That's what we would like to look for. We would like to have more such results, right? It's something which is very intuitive, just a wave transform. So this is the dispersion of my spin waves P and epsilon of T, just the cosine. And this is called the Fermi weight, 1 over 1 plus E. So you get the wave transform of the Fermi weight for multiplied by the same thing for weight expression. But in general, if you have interaction, things will be much more complicated. You will not have, here is super selection happening, so you have very reduced scattering. You have only 2 integrals. In general, you will have, if you do a form factor expansion, a series over more and more integrals, and you can't expect to have such nice functions. Usually you'll have functions which are defined in terms of solutions of linear and nonlinear integral equations, even in the integrable case. But, I mean, if you have such a thing, you can evaluate this numerically, and you can do asymptotic analysis in all the parameters. Here's a picture. What you can do, so here, the black line, in the black line I plotted these correlation functions. I can do that using Mathematica. And then I did a subtle point calculation, so you see that the asymptotics in x and t in space and time splits into 2 regions. There is a light cone, there is a time-like regime and a space-like regime, and the typical Stokes singularity where they meet. So this is, on the one hand, I mean, this shows you how powerful this subtle point analysis is. On the other hand, it shows you typical behavior. So if you introduce interaction, the formula are much more complicated, but the physics will be the same. So the curve will be qualitatively the same. So what you see here is what does this dynamical correlation function do? It describes this, the spreading of a local perturbation generated by a local operator and time evolved with the Hamiltonian, and the system is equilibrated by its interaction with the bus, right? And so what happens is typical wave dynamics. So it's the same as when you're sitting in a boat in a pond, and you can measure you feel the waves, and the frog jumps in. So then you wait some time, nothing happens. Some waves approach you, and after the time, your boat will get a jump, and then this jumping will relax. And this is what you expect, and it will be always like that. But you want to know this function quantitatively, right? Okay. So how can we do that for integrable systems? I'm thinking in terms of vertex models, and we use something which I like to call a lattice path integral. It's of course just a vertex model partition functions, which do insertions, which are our operators. And here the spectral parameters are all 0, and here I use alternatingly something. I mean here, so this is any R matrix. Still, I'm not talking about XXZ here, but any solution of the Baxter equation which is regular, so which reduces the permutation when you put the spectral parameters to 0. And in this R matrix, you put, I mean, you assemble this nice picture, and then you put all these spectral parameters equal to 0, and here this is a double row transfer matrix, and if you have put in small numbers for the spectral parameter here, for instance, some TR, some time in scale set by the R matrix divided by n, then you find for large n that you have this. So this becomes the time evolution operator, the double row transfer matrix. And if you insert a set of this little t1 over capital T is the temperature, you can also do the ensemble average, right? So you time evolve your operator x adjointly, so you have t, you have minus t, and you do the averaging. That is very intuitive, and that's what you expect from a path integral to do. Please.
Do you have any restriction on your operator x and y?
What do you mean by restriction?
Should they be point-like operator, or it should be short-ranging operators?
We are on the lattice here, so the only thing is that they extend over a finite number of lattice. Any operator.
But more than one is possible.
Yeah, that's the point here.
Okay.
Yeah, so that can be more than one. And this realization here, of course, everybody could guess it, but in this specific way, and in the context of the X equal, this was first used by Kazumitsu Sakai in 2007, right? So then this object is a double row transfer matrix, and this object where you have a staggering is called a quantum transfer matrix. So the vertical one I call quantum transfer matrix, and this I call double row transfer matrix. And I will expand everything in terms of data of this staggered form. It has eigenstates psi n and eigenvalues lambda n, and I'll crucially use this ratio of eigenvalues, rho for ratio, so lambda n over lambda 0 is one of my most important inputs, and I have the states here. That's all. And then just for, I mean, not everybody is used to this transfer matrices, so the double row transfer matrix is familiar to everybody, so it gives, it approximates the evolution operator, and if you apply periodic boundary condition on this side and do beta ansatz, what you are doing is you quantize the momentum, right? And so the beta ansatz equations are momentum quantization conditions for this interacting system, Hamiltonian is Hermitian, and the beta roots are continuously distributed in the large lattice limit, large volume limits, and for L to infinity described in terms of linear integral equation. As opposed to this, is T naught, so the vertical transfer matrix describes space translation, and if you apply periodic boundary condition in this direction, then in the limit of large n, your beta ansatz equation become quantization conditions for the energy. This corresponds to a big rotation. You have time and space corresponding to momentum and energy. So you're now quantizing the energy, and you have rather different beta equations, different eigenstates, and a different basis, which may be more useful than the Hamiltonian basis, or less useful. You'll have to see, right? I want to advocate the point of view that it is more useful, right? This is a non-Hermitian transfer matrix. The eigenvalue ratios are non-real in general, and they describe oscillatory behavior of correlation functions in the space-like regime. The beta roots are usually not continuously distributed in this limit n to infinity. They are not continuously distributed, but have some limit points. They are only continuously distributed if you send the temperature to 0. And at every non-zero temperature, the distribution of these beta roots is described by nonlinear integral equations. Nonlinear, linear, right? So, then what we do, I go back. So what we do is we want to express this partition function in terms of data of this quantum transfer. So what we do basically is we use some identities which allows you to flip this operator. This is sometimes called solution of the inverse problem. Then we use the inhomogeneous shift operator, apply it n times to move it here and flip it back. Then everything is on the same level here, but we have n additional lines, which is bad because we want to send n to infinity. So in order to deal with this situation, we insert a the composition of unity here and get an expansion in terms of eigenstates of psi n, right? So if you do that, this is my notation for the operators, fancy notation. I assume I'll have U1 symmetry, and if you do it then for these operators, x which extends over L side and y which extends over R sides and has distance m from x, you find such a formula. So this is a formula where everything is, say, expressed in terms of beta ansatz data. Beta ansatz data means eigenstates and eigenvalues. So the lambdas are the eigenvalues, the pi's are the eigenstates, and those rows were the eigenvalue ratios. And you see, so one thing, what happens here typically, and which is an advantage compared to the Hamiltonian basis, is that the trace which you need for your statistical average reduces to taking an expectation value. This is because your transfer matrix in vertical direction, our quantum transfer matrix, is gapped, and if you have high powers of it, they project onto the dominant state. This is this psi naught, ground state of this vertical transfer matrix. So there's only a single sum here, and in the other case you would have a double sum. Single sum is the first advantage of using this quantum transfer matrix. Fine. So you have dominant state here, excited states here. And this is generally valid. So this is not an XXZ thing. For the Hubbard model, you have the same formula. For any other model, you take any other vertex model, which has the property that the R matrix, when you set the spectral plot is equal to 0, is the permutation. This is the only thing which is used here. Plus, of course, for the mathematicians, some analytical properties, so it has to be differentiable at 0, something like that. That's all. So then, what is the problem with this formula? First of all, you have to compute these things like scalar products, eigenvalues, these expectation values. But then the second problem is you have to sum over all excited state. And this is actually a big problem. Why this is not totally applicable and why in the end I can say something only about XXZ because it's the only model where I have sufficient knowledge about the spectrum. Let's see. But still, well, we were using that for the case of length 1 operators and got nice results. As I said, we're doing this for several years. And the new point in this talk, or last year, what happened last year, is that I extended the length of the operators. But then the problem here is that the normalization is not natural. So why is it not natural? If n is equal to 0, then this object has a very nice property which is called reduction. If you take the trace with respect to the first of these of the spaces in this project, then you get I mean, this means to set x1 equal to identity operator, then you get the transfer matrix here, and then you act to the left, get an eigenvalue, and that kills 1 power here, and you get the shorter object. This is called reduction, and you can do it to the left and to the right. And if you have psi n equal to 0, it works. But if you have excited states here, there is no reduction because the normalization is not good. So what you would like to have is you would like to divide by psi n psi naught. But this is 0 due to the ice rule, so it's bad to divide by 0. That's why you have to find the way out, and the way out is extremely simple. You have to, those two, I mean the two states, the transfer matrix itself, it has this U1 symmetry, and it comes with, you can couple a U1 field, which I call H here, the magnetic field, and if you choose the fields differently, so for the ground state you take H, and for the other one H prime, and this is generally non-zero, and you can divide by it. So you divide and multiply, and then everything is expressed in terms of the following quantities. So by dividing and multiplying, you get something which I call amplitude or universal amplitude. We still remain with the rows, and we have two objects which are now, as I claim, properly normalized form factors. Fyodor was not using them for years already, but it took me time to understand that I have to do the same thing. If you look at the Saint-Gordon paper from 2011, they're using the properly normalized things. But here for the spin chain, it also has to be done. So,
excuse me, can you draw a picture for this form factor? Only for the form factor?
Yes, I can. You want me to do it now?
No. Then you can explain it afterwards.
I'm just in a hurry. I'll explain you. But you will see, I'll talk about this a bit more and you will understand more. Unfortunately, I didn't do it in a pictorial way. Many of the results I'm going to show you were obtained by drawing pictures. But, I mean, typesetting pictures is the problem, right, with LaTeX. I prefer formula. But I can draw it for you at the blackboard later. So then using these functions, we can, and now I specified my operators to matrix units. If you take matrix units here, they form a basis, then you get some objects here which form bases of form, right? So that's it. So you have only these properly normalized form factors. You have eigenvalue ratios. Eigenvalue ratios I don't care much for, so they were investigated by people like Andreas 30 years ago. They are controlled, well known. But those form factors are not so well known, and the amplitude is also generally not easily calculated. Remark, when n is equal to 0, now these objects turn into this reduced density matrix with different magnetic fields, and this was a very important object studied intensively in the literature. by means of the algebraic Bethe-Ansatz and especially by means of the fermionic basis approach. So the protagonists here are both Jimbo Miwasman of Takayama, and there was a series of papers. Not all of them are listed here, but only those which I considered the milestones. This is where the fermions appeared. This is where the creation operators appeared. This is where the completeness was shown, and this is what we call JMS theorem, so the nice properties of the creation operators. Right, and so what I want to say is that these form factors have the same properties, right? So that's the take-home message. The form factors here, if they are defined like that, can be computed by means of the fermionic basis. This is message number one. The message number two, I can also compute this amplitude in certain cases completely explicitly, and this gives you completely explicit series representations which are very efficient for calculation. So let's go there. First of all, for the mathematical properties, what I want to do, maybe I don't show you these formula. I show you back again the picture. So I wanted the picture. So what now for studying the mathematical feature, I generalize this. Here I have these special values which allow me to temperature and time, but I'll consider just any distribution of inhomogeneities here, which I call nu. And here I have a staggering back, forth, and I consider any collection of directions, which I define by plus minus, or by assigning a vector of pluses and minuses, right? And then I get the thing which I can characterize by its properties, which is here. This is now what we love, so it's a very general object, and we can study its properties. So, and you've seen some of this in talks by Hermann, by Henrik, also and by Holger. So what are the properties? Let me repeat it. So there's normalization, right? That's very good. So if you take the trace over all vertical spaces, you get 1. But there is also reduction. If you do it only with the first space, with the last space, it reduces to the object which is one side shorter. If you want to do the same thing with the first side, you have to introduce such an operator q to the plus minus sigma z because of the different magnetic fields, and then you get this factor rho n. Rho was this eigenvalue ratio. So, and there are two types of form factors, plus and minus, depending on whether the excited states is left or right, and you get rho or 1 over, right? This is very important. Then you have other more natural properties, of course, Yang-Baxter symmetry or exchange relation, U1 symmetry. It's not important to understand this in all detail now. There is the crossing relation or rho reflection. So the sigma is saying in which direction my arrows go is pluses and minuses, and iota j reverses it in the j line, and at the same time you replace nu on this line by nu shifted by the crossing parameter. This is a symmetry. The rows are all commute, so you can act with the full symmetric group on the rows. You don't change the object. You have a nice connection between the plus and minus correlation function if you transpose and reflect. So this is kind of TP property. They go over into each other, right? So they are not really independent. Then you have the meromorphic functions. You have asymptotic reduction. This is something you saw Holger's talk. So if you send one of the parameters to I or plus minus I infinity, you also reduce the object and get some trivial factor out. And then there is the major equation, which is a variant of the reduced Knischnik-Samologikov equation. So this is what was used in order to obtain the fermionic basis. And this discrete version was introduced by Ritter Aufgebauer and Andreas Klüber. So the only change here is how this, I mean, now it's for excited states, so somewhere must be the information for the excited state. So this equation is something you shift by the constant parameter, and then there is this operator which was A in Henrik's talk. So some linear operator acting on F, and this you can express it in terms of the monodromy matrix F1. So usually people consider this when there was 1 here. Maybe when there is a twist, it should not be 1. But anyway, so even if H is equal H prime, as soon as you have excited states, this is where the information of the excited state is. There's the eigenvalue ratio. Right, so that's one way of characterizing these form factors. Well, we want to calculate them. And so the simplest ones, those which are most useful in condensed matter physics applications, can directly obtained from these relations. So in principle you can use also the beta ansatz. I'll talk about that a little bit later. But the beta ansatz is really a complicated, hard method. So the simple form factors can be obtained much easier by using the relation, right? So maybe I go back and show you this is a calculation. Show it. So here we have the reduction relations. When m is equal to 1, then on the right-hand side you have the identity here. Identity means 2 by 2 identity matrix, so the matrix 1, 0, 1. And here you have these numbers. And here you have the trace, so you have the matrix 2 by 2, which due to the Ice rule is just A 0, 0, D. So A plus D is 1, and Q to the alpha A plus Q to the minus alpha A is rho. So linear equation which we can solve. And this sounds ridiculous, but you get a valid result for the form factors here. If you want to do this by beta ansatz, you work for days, right? Hard work, and we get it by solving a linear equation.
So you are doing a form factor bootstrap.
In a sense, right? Yes, yes. On the lattice, in a very generic situation with finite temperature, even time is involved. So all these objects depend on time actually before you do the quota limit. So then you insert it back into the formula, and we have divided it by something which goes to 0 when you send magnetic field H prime to H. So that means that this amplitude has a double, it goes to 0 quadratically in H minus H prime. So if you send H to H prime, then you pick up the second term in the Taylor expansion. And you see those guys, alpha is H minus H prime, so those guys have a first order pole there. And it cancels out again, and you get something nice, which was actually known in this form, but it was not known that you can get it like this, easy. And you can continue the game. This is a very special operator, and now it ranges over 2 sides. It is very interesting from the point of view of applications, because it's the spin current operator. So sigma z is the local magnetization, and you have a continuity equation for the local magnetization. So change of magnetization is divergence plus divergence of the current is 0, and this is the current operator, right? And this is, if you know the current, you can understand spin transport in these spin shells. Spin conductivity, things, there are hundreds of papers on these things in condensed matter physics. Numerous fruitless debates, and you can get things exactly, right?
Is it a conserved current?
Pardon?
Is it a conserved current?
No. I mean, of course, in the sense that you have a continuity equation, yes, but not in the sense that the sum over local density commutes with the Hamiltonian. Those are different concepts. Those are different concepts which are sometimes confused. This special operator has the property, it's a special combination of of matrix elements of the two-side density matrix, and this special combination can be also obtained by just using the reduction plus Young-Wechsler symmetry. But this is the only operator. If you want to have the full two-side density matrix, you need more. Okay, so in that case you get, again, for your form factors, here is something which is second derivative of A times the simple function, only expressed in terms of the eigenvalue ratios. Here is the logarithmic derivative. Then, so as said, you can also do things by beta ansatz. Some people like that, others don't like it, or it can be done. And if you want to do beta ansatz and then do the Trotter limit, then you come to nonlinear integral equations. I can probably go over it only in a way that is too quick to learn as if you didn't know it before. So there's an integral equation which has three main inputs. One is the driving term, which this is called the bare energy, some simple function. Then there is a kernel, which in my parameterization is the difference of two cotangent functions. And then there is an integration contour which selects the excitation for you. And so we choose this integration contour such that 0 is inside, and the contour must be narrow enough so that if lambda is inside, then lambda shifted by plus I gamma must be outside, and we choose a zero monotony contour. And so the collection of these contours parameterizes the excitations. So this is one. Number two is a function we like. This is a function satisfying the linear integral equation once the solution of the nonlinear integral equation is known. The solution of the nonlinear integral equation is this A. So 1 over 1 plus A is the generalization of the Frobel function, which you found in my simple formula to the interacting case, and rho also appears here. Then there is this funny deformed kernel where alpha is alpha deformed. Alpha was the difference of the two magnetic fields. This first term is a deformation of the bare energy by alpha and by this eigenvalue ratio. Anyway, so then you can, except for this measures m, you can define some conjugate measures m bar, and you can write down a multiple integral representation for that. The interesting thing is it looks exactly as the one for the reduced density matrix, except that everything is deformed. The contours are deformed, the measure is deformed, but formally, if you replace the letters by others, it's the same expression. Right? So, the input is the solution of the nonlinear integral equation, this function g, which plays a central role, and then something which looks like wave functions of beta ansatz. This is well known, was first obtained for the reduced density matrix, so zero temperature by Jimbo and Miwa, and then re-derived by several other people in this most general setting by Hermann Bose and myself in 2009. Right, so then you can use that, and the claim is that, so we want to connect this with the fermionic basis, and one way of doing it is to get this two-side density matrix, which is written here, while we want to have it as a single integral, and it turns out that those integrals factorized by some tricks, which we developed a long time ago. So the claim is that for m equal 2, so the all neighbor correlators are all neighbor form factors which have only operators of length 2 can be expressed in terms of two functions. Here they are, some integrals. This integral can be calculated in terms of the function rho, which was not easy. Also something I did together with Hermann some time ago. And the other thing has never been further simplified. Then omega, according to the papers of both Jimbo Miwa, Smirnov, and Takeyama, can be defined is the trace taken with the two-side density matrix and these beautiful fermionic creation operators acting on the identity on the line. So we have the expression for the two-side density matrix, which I don't write you because it would cover 2 or 3 slides and you will not be happy anyway. And we have similar complicated expression which will cover 1 slide for these operators, for how they act on 2 sides. Anyway, you have to put it into Mathematica, then take the trace, and then it pops out the function omega in terms of psi and rho. Right? That's the answer. And then, since we have this Stirnböhm-Smirnov theorem, we can get all form factors of arbitrary length expressed in terms of some rational coefficients, which will be generated by the fermionic basis, and derivatives of this function omega and the function rho. And the simplest example where rho p is the example, again, physically important. This is the energy density, so this is delta, and sum over these operators is the Hamiltonian, so this is the energy density. And of course, this is a measurable important quantity, which is Goehmann scattering or in experiments, something you want to know if you're an experimentalist in condensed matter physics. So here the answer is, again, the same thing. We get the second, now you should already be used to it, the second derivative of A with respect to H prime. And then here, now this is a difference with the density matrix case. Now these guys omega are also singular. They have poles in alpha of first order. And one interesting question to Hermann, for instance, is I mean, here, this formula shows us how to get out the pole from phi. Now my question is how to get out the pole from psi, right? It's, I think you're working on very similar things, and you were mentioning things which may be related to our old paper. Your operator's H, maybe do this exactly, should discuss this. Anyway, so this is the question here, how to extract this more explicitly. Let's go to the calculation of the amplitudes. For the amplitudes, I don't have nice functional equations. So the amplitudes were calculated by beta ansatz so far. I mean, and in a sense they are very simple elementary objects. Such objects have been studied not only by us, also by others. By beta ansatz, there is this scalar product formula of Slavnov. So you have 4 scalar products. You apply this 4 times. And you can bring it into this form, which I like most, where everything is, again, expressed in terms of the functions I like, eigenvalue ratios, bare energies, and these auxiliary functions. Here I have chosen a notation where A refers to the dominant state and AN to the excited state. The lambdas are the beta roots of the dominant state, the mu's of the excited state. So you have this kind of norm determinant, there is a Cauchy determinant, you have this 2 times from 2 factors in the product, and the numerator you have something else. And then the task is to analyze this for n to infinity. And this is not easy. Actually, this is the paper, the contents of the paper we wrote with Konstantin Babenko, Kozlowski and Suzuki. And so there are severe simplifications happening in this case, delta larger than 1 and when t goes to 0. So generically, if you start from large determinants and make the matrix larger, you expect to get something like Fredholm determinants, right? But in this case, we can evaluate them. So what we do is basically, first we separate particles and holes here by some procedure by hand, and then there is after we have extracted the particles and plugged in the holes, there is something which has some root pattern which has no holes, and then we divide those things here, get some determinant of a large matrix G, and then we replace this by the right-hand side of the integral equation and pull out the driving term. So what happens that this driving term can be calculated explicitly. It gives you an elliptic Frobenius determinant, and the rest is of the form 1 plus something, plus some complicated operator. But this complicated operator has the property that it exponentially fast goes to 0 when temperature goes to 0. So in this limit, we get the Flaton determinant of the identity operator. So we have the identity operator. This is the Flaton determinant we can calculate. And this drops out, and we remain with something theta, Jacobi theta function. This is a difference of the sum of Goehmann's particle parameters. This is a big ratio. I don't give you the details. You will suffer more in a minute. I show you some explicit formula, but here I just describe it. Here you have ratios of Q bars and Q gamma functions, and these are determinants of size L. L is the number of excitations of particle and holes. We're in the spin 0 sector where you have as many particles as holes. L. Two determinants, and this determinant, I call this omega because it has some resemblance of the function omega. So it's some inhomogeneous term plus an integral with a measure of Q gamma functions and then the elliptic functions which look like this G function. Very nice thing. And here you have a 2L by 2L determinant which is made up of this auxiliary function A, derivatives of the auxiliary function. And this really acts as a measure. So using this denominator, you can interpret this expression as a multiple residue. You have to sum over all of them. Summing over residues gives you a contour integral. Summing over multiple residues gives you a multiple contour integral, right? So then you get, instead of, so you can do the summation over all accepted states. And I mean, this is a long paper, 50, 60 pages with very technical calculations. Believe me, I cannot tell you everything in a short talk, but the answer is very simple. So, and then after going from sums to integrals, it becomes even more simple. And in this limit, t to 0. So we are in this massive regime, which also means that the magnetic field shouldn't be too large. Temperature has been sent to 0. So what happens to our sum over excitation? It becomes the sum over classes of excitation. And in every class, we integrate. So classes means one particle, one hole, two particles, two holes. And within this class, we have an integral. So U's are holes and these are particles, right? And this U, capital U and P is the set of all particle and hole properties. And so this here is what happens to this eigenvalue ratio. If you take the limit t to 0 and this eigenvalue ratio, this complicated things, sending also n to infinity, you use the Euler formula and get such a nice thing where p is the momentum and epsilon the energy of the excitations, right? And then you have an amplitude here, which is parameterized by the excitations. So I'm sure, yeah, right.
How much time do you need?
I will accelerate. Now come the complicated formula. I mean, it depends also, yeah. Yeah, let's go a bit faster. So this A is an amplitude, and this is basically what we had on the last transparency, except for the measure. The measure has been digested by the integral. It's gone, but the other thing is there. And of course, this depends on the operators. I call it AXY, and the nice interpretation. This is a superposition of waves like in electrodynamics, but now you have interacting waves, right? This is the picture. The contours are simple. Just intervals from minus pi on 2 to pi on 2, shifted a bit up or down in the complex plane. And the two simple cases I just showed you, that's where only rho appears, is when we have sigma z correlation functions, or the current correlation functions. They're both equally simple, right? And this was published with my colleagues in two papers. And let's see how the result looks like. Now I just describe the result and show you some pictures, right? So this is first of all the dispersion, and it's a rapidity representation of the dispersion. This is one of the beloved functions of all undergraduate students. Everybody knows this. This is the solution of equation of motion for a mathematical pendulum when it goes over. This is the end, so this is a soliton under periodic. Together they compose into a massive dispersion relation on the lattice, which means we have it's bounded, right? Then I use this fancy notation. I already used it without telling you. So sum over parameters and the difference of the sets means this difference of the sums, and the same for the product. So our amplitudes, again, as you may have expected, they factorize into two parts, one coming from the universal part of our amplitude and the other coming from the operator. And look what happens to the operator part. So that was this rho n minus 2 plus 1 over rho n. This becomes sine square of some of the differences of momenta. And this rho prime over rho square, the logarithmic derivative, becomes square of the sum of the differences of the energies. Beautifully simple. This is the part which comes from the form factor bootstrap or fermionic basis in this very simple case. And so we have to, the remaining part is this weight. So I have this, and the point is we can entirely describe this in terms of known classical special functions. The functions which occur here are of two classes. One is basic hypergeometric series, or Q-deformed hypergeometric functions. And they are, well, I mean, so if Q is 1, if Q goes to 1, this becomes the generalized hypergeometric function. When L is 1, this is, and Q is 1 is the Gauss hypergeometric functions, and you have a multiparametric generalization which was introduced by Eduard Heine in his Theorie der Kugelflächenfunktion in 1846. Right? So classical stuff, studied for many years. And we multiply this with some product. This gives us a function psi. So we will have phi 1, you need phi 1, and the function psi, which is phi 2. Those are special hypergeometric functions. And we multiply just by something which looks like factors you know from the beta equation. And we have a conjugation, which means we interchange parameters. So we invert the sign of all whole and particle parameters. Right. Then we build a matrix out of this. So this matrix has the function phi on the diagonal and the function psi, or linear combinations of psi and psi bar on the off diagonal. Where here these coefficients are ratios of Q gamma functions. Sigma is the difference of the sums of whole and particle parameters. And then we introduce this ratio of Q bars and Q gamma functions, right? So Q gamma square, Q gamma and Q bar square. And then we put everything together. That's the answer. So this is the universal rate. It is explicit special functions. So here are Jacobi functions, products of gamma and Bart's functions, determinants which have the basic hypergeometric integrals inside and the quotient. You have to compare this with things that were known before. If you open the book of Jimbo Miwa, this thing is it's a sum over 2L over L summons, which are multiple integrals, right? So we have to have, in a sense, we have calculated these integrals and summed up an exponentially large number of them. And this gives this answer. Right, and it's computationally or numerically efficient, so you can evaluate it using steepest descent, numerical steepest descent method. You can get this for any time. You can calculate the asymptotics by saddle point methods. And so this is DMRG. DMRG is good for short times, and you see that it compares well. But we can go to long times, and we can go to where you want a time, which nobody can do numerically. We can Fourier transform it and get structure function. This is what is measured in neutron scattering experiments. And we can also do it for the conductivity, for the current correlation functions. And when you do the Fourier transform there and look at Q equals 0, you get the conductivity. This is really conductivity. So this is something condensed matter physicists dream of, to calculate an optical conductivity more or less explicitly. And it has a contribution of 1 particle 1 hole, 2 particle 2 holes, and the higher contributions, they drop off dramatically. They are factors of thousands. So the 1 particle 1 hole excitation here can be obtained. The Fourier transformation can also be done analytically. There we have some tools from mathematics. There is a nice, it's a Q-Gauss identity, so something like Rogers-Ramanujan identity. You can transform bumps into products and things cancel. We end up with fully explicit result for this optical conductivity expressed in terms of Barnes function and elliptic function. Right. And that was it. So we have developed the thermal form factor approach to the dynamical two-point functions of arbitrary local operators and fundamental integrable models of Young-Baxter type. We found factorization into universal amplitude and properly normalized thermal form factors for spin 0 operators in the XXZ chain. And the properly normalized form factors have properties very similar to those of the generalized reduced density matrix. They satisfy a form of RQKZ equation, and they can be represented as multiple integral factorized. Here, look at from an old talk, the relation with the fermionic basis is not mentioned. It should be added. And we have applied our approach to the dynamical two-point function of the magnetization of the spin current for the XXZ chain of the massive regime and at the low T limit. For T to 0, we have obtained explicit expressions for the form factor amplitudes that contain only finite determinants and no additional summations. The resulting series are numerically highly efficient. Right. Thank you very much.
In some moment you show correlation function in coordinate representation, like there was this dependence on m, yes? Like distance between two operators. So is it here asymptotic, so it applied for any m, including small
You mean the
m?
pictures? What do you mean? The pictures or formula?
Formula, of course.
Everything is for every m.
Ah, okay.
This is for every m, for instance, or every L, no, it's called m. L is the number of excitations, sorry.
No, yeah, for m small, distance between operator, isn't it?
I mean, you have to distinguish between length of the operator and distance. So
Distance between operators.
So the distance between operators is arbitrary. So,
Okay.
yeah. So it enters only here. It's a parameter.
Yes.
The point is, as opposed to numerical approaches, so these formula become the simpler or the easier to use the larger m. So, I mean, this is an asymptotic series. It has the property that when m is large, you can basically forget about all integrals except for the first one. This is what you can see in the pictures.
So at small m you expect problem. This is like was.
I show you the problem, the size of the problem at small m in the picture. So I said at large m, one integral is enough. So at small m you can use DMRG, and here we have the red points is one integral, which is enough for large m, and the black is DMRG, and you see the error here, the numeric, so not the numerical, the error. So the difference from this approximate result to the DMRG result. Then you calculate the second integral, then you have the green dots, which lie already even for
Okay.
t equals 0 on the curve. And you can add the blue dots, and, well, I mean, if you're good at numerical integration, you can go higher here, right? So, but, I mean, I also have to say, I mean, this is for the massive regime. If you go to the massless regime, completely different story. It's much more complicated to sum things up. So this also is so nice because we are in the massive regime. So we are thinking about the massive regime for already some time. And I have hope that we can also do something, but it will be more complicated, right? So but I mean, another thing, maybe I can say one more word. So this is really based on the fact that we have simple beta root pattern. So I call this, and on this slide, I invented the term no string hypothesis. So by studying these,
String hypothesis has nothing to do here. So
No,
for Sine-Gordon model, you have, if you wish, string hypothesis, but the four factors are given in factorized form without any problems.
so what I say, I call it no string hypothesis.
In Sine-Gordon, I have
String, yes.
But so this is this kind of mistake. So you can write formula with factorized interval.
Yes, actually, this is one of, I know that from your work. So you have, you change the contour, then the strings are gone, right? Something like that?
This is not like that. We just this is a good base. You see, strings appear when you solve beta ansatz equations, and then you have high level beta ansatz,
Yes.
and stupidly you start to solve it, continue solving,
Yes.
but you should not.
Yes, that's exactly what we did. I mean, if you use the usual transfer matrix, that was an earlier paper, then we run exactly into this problem.
Earlier paper, I mean this paper from 80s, but it can not be early. But what I mean is what from the very beginning the four factors were given in factorized form. Then there was a mistake of evolution when the multiple integrals are introduced.
Yes.
And now I am very happy that everything returns to the
Yes. Yes. Well, what I wanted to say, we are achieving it here by using the spaces of quantum transfer matrix eigenstates at finite magnetic field, and it simply doesn't have strings. And what we found recently, or the last year, which is unpublished work, is that this is also true in the massless regime for data between 0 and 1. So we can do the same thing. Well, you would know that, but maybe other people not. I mean, it really was hard to find it out.
Question from those.
So what is the physical meaning of this capital W?
A good question, yeah, that's what I asked you. And I would also, I would be interested to understand what it means in field theory, actually. That would help to find the meaning. So, I mean, we have the four factors, it's a clear thing, but this universal amplitude, which, as you see, is the much more complicated part, right? But it is the same for all, this is independent of the operators. It depends only on the spin. This is the answer for spin 0. I'm very much interested to find this function for spin S, for any spin. This would be my dream. I mean, this is also what we're working on, but I don't, at the moment, yeah. We'll try to use screening operators probably, which were introduced by those gentlemen. Well, I'm not sure if we can achieve an answer like that. We have to try, right?
If you calculate ratios, for example, this guy disappears.
What?
If you calculate ratios of form factors, or
Then they disappear.
then
Right?
they disappear.
That's the point. It's a kind of universal part, but it was hard to get it. Yeah? Especially the last part. I mean, the point is that I didn't tell these technical things, but one of the points is it depends on alpha, right? And you have to take the second alpha derivative. Everything is naturally given in terms of determinant. Nobody wants to take derivatives of determinant. When the whole structure, the beautiful structure collapse, you end up with sums. This is very, very nice. So the reason why this is so nice is that we found a factorization of a determinant. So, which is it's a very miraculous thing. So here, in this formula, you have integrals, right? And if you can then calculate them by residues, and you get hypergeometric functions, but the true mass. And then you need some hypergeometric function identity to simplify that. this. If you find this identity, then you see that the matrix elements, you see that it's a product, the matrix elements belong to a product of two matrices, so you can factor it again. And one is again an elliptic Frobenius determinant of a type that it spits out a factor quadratic in alpha. and everything becomes much simpler. But this identity was not in the book of Gaspar Raman, and we asked experts like Ole Warner, they didn't know it. And it took us months to find it. It was the longest part of the calculation.
Because it's not very easy to see what the limit corresponds, would correspond to, for example, sine Gordon.
Yeah,
If you can reproduce further the result, for example, for sine Gordon.
I mean, in the isotopic limit, when you do a scaling limit, you can find a special point of sine Gordon.
So it's here somehow. It's here.
Yeah, but the isotopic limit is again singular here, because I thought it would be easy, but what happens in the isotopic limit, in the isotopic limit, all these limits exist, Q turns, and so the Q hypergeometric series become usual hypergeometric series. But it turns out that these matrices have one linear relation. So in this, if you do the limit, you find a relation among hypergeometric functions, probably unknown, among n of them, of the form determinant is 0. And you know that the matrix has rank L minus 1. So it's a very complicated hypergeometric function identity, I think it's not known, which, but it leads to the fact that so this goes to 0 linearly, this also, and this has a pole. And again, you have to find a good way of getting a nice expression from that. All right.
I think people are hungry. Let's